Moving on to measures of dispersion, here we will talk about the range, mean absolute deviation, and then variance and standard deviation. While all these measures are important, the most important measure in the field of finance is variance and then the square root of variance, which is standard deviation. In any case, let's start with the concept of range. Range is simply the difference between the maximum and minimum values in a dataset. In other words, we can say that the range is a number which is the maximum value minus the minimum value. If we express this in words, we can say that the range of this data is from this certain maximum value to a minimum value. If we are given this data, what is the range? So quickly come up with the answer before I give it to you. Here you look for the lowest number and the highest number, and one way of expressing this is that the range is 25 minus 5, which is 30, or we can say that the range is the maximum value to the minimum value. So we can say that the range is 25 to minus 5. The advantage of this measure is that it's very easy to calculate, as we've seen over here. The disadvantage is that it only considers 2 data points. So if we have lots of data somewhere in the middle, so lots of data, let's say, is between 5 and 10, but then there is one data point that's minus 20 and another data point that's plus 150, then the range will be from 150 to minus 20. So the range will be 170, even though most of our data is contained here between 5 and 10. So that is the disadvantage of this measure. It only considers the lowest point and the highest data point. Our next measure, which does consider all the values in a data set, is the mean absolute deviation, or MAD. This is the average of the absolute values of the deviations from the mean. Here is the formula. So notice we need to calculate the mean. If we are coming up with the MAD for this data set, step 1 would be to calculate the mean. Then we take each value. From that value, we subtract the mean. So xi represents each of these values. We take this difference. We come up with the absolute value. Then we sum all the absolute values and then divide by the number of terms. In this example, n is equal to 5. Now, I want you to calculate the MAD before you look at the solution. So hopefully here's what you did. Step 1 was to come up with the mean, that's 8.6. Then we take each term starting with 8. So we do 8 minus the mean, and then we take the absolute value, which is 0.6. We then have 12 minus the mean, and then the absolute value is 3.4. So 12 minus 8.6 is 3.4. That is positive, so we take that. And so on for the remaining terms. We sum all these 5 values and divide by 5. This gives MAD equal to 1.92. Moving now to sample variance and sample standard deviation. The variance of a distribution is defined as the average of the squared deviations around the mean. When we just say variance, we are typically referring to a population variance. Now, with respect to variance, it is more common to calculate what's called the sample variance. The sample variance applies when we are dealing with a subset or a sample of the total population. And generally, since populations are very large, we will be working with samples. The formula for the sample variance is shown over here. So S squared refers to the sample variance. If we are talking about a population variance, that will be denoted as sigma squared. Generally, we use Greek letters when describing a population and regular letters such as X for mean or S for standard deviation or variance when we are working with samples. So notice here, step one is to calculate the mean. So if we have this data set, we would have to calculate the mean. We then take each value. From that value, we subtract the mean. We then square. And this is done for all the values. So for each value, subtract the mean and square. We do the same for the next and the next and the next and the next. All these numbers are added and then we divide by n minus 1. This n minus 1 is important when we are working with a sample. Then dividing by n minus 1 ensures that we get a more accurate result. So you simply need to memorize this formula. Now using this formula, I want you to calculate the sample variance. So hopefully here's what you do. You've calculated the mean earlier. The mean is 8.6. We take each number. From that number, we subtract the mean and square. This takes care of the negative issue. So when we have a negative number here, by squaring, the negative goes away. So we take our 5 numbers and add them. And then we divide by n minus 1. N is 5, so n minus 1 is 4. And we get our variance, and more specifically our sample variance, which is 6.8%. This is a measure of how spread out the data is. So notice here, clearly our data is spread around 8.6. So that's the mean value. Our numbers go down as low as 5 and as high as 12. This number, 6.8%, is a measure of how spread out this data is. Had our data been more spread out, so for example, if this number had been 20 instead of 12, then the variance number that we would have calculated would have been higher. And you can see that from this formula, because if instead of 12 we had written 20, then clearly S squared would be a higher number. Now S squared is a squared number. Often we want something in terms of regular numbers. So for that, we use the sample standard deviation. The sample standard deviation is simply the positive square root of the sample variance. So in this case, when we take the square root of 6.8, we will get the sample standard deviation. You might recall from earlier in this reading that I said that the geometric mean is less than the arithmetic mean. And I said that this difference becomes larger and larger as the variation in data goes up. Now we have a formal measure for variation, and that measure is literally the variance. So this relationship actually quantifies the difference between the geometric mean and the arithmetic mean. So notice that the geometric mean is equal to the arithmetic mean minus the variance over 2. So just try and remember this, though the probability of being tested on this formula is low. What you do need to remember, however, is that the geometric mean is less than the arithmetic mean, and as the variance goes up, this difference increases. On this slide, I'm showing you how to use the calculator. So if, for example, we have this data and you need to calculate the population and the sample standard deviation, here are the keystrokes. I want you to actually practice this, because on the exam, if you need to calculate the variance or the standard deviation, it makes more sense to use the calculator versus using the formula. But there are some important points to note over here. The calculator will give you the sample standard deviation and the population standard deviation. So this is a symbol for the sample. This is the symbol for the population. Now, if the question is asking for variance, then you need to square these terms. So if the question says, what's the population variance, then you take the population standard deviation and square it. So keep in mind that these are the standard deviation numbers, not the variance numbers. Moving now to a practice problem. So you are given this data and you need to calculate the sample variance. Now you can use the formula, or you can use the calculator, or you can do both. And here is hopefully what you get. So you need to first calculate the mean if you are using the formula. Then you add all these differences which are squared, divide by n minus 1. This is cumbersome, so I would suggest that you try and get this answer using the calculator. And remember, on the calculator, you will get the standard deviation. You will have to square that standard deviation to get this number. The standard deviation measures deviations on both sides of the mean. So if this is the mean, we have certain positive deviations and negative deviations, and the measure that we calculated actually considers both the positive and the negative deviations. The target downside deviation, which is also called the target semi-deviation, is a measure of the risk of being below a given target. So this particular measure only focuses on the deviation that's below a certain level. And the reason this measure is used is that often investors are concerned with the risk of being below a certain level. They are not concerned with the returns or the numbers being above this target level, and that's why we need to understand this particular measure. One point is that this measure is also called the target semi-deviation. This measure is calculated as the square root of the average squared deviations from the target. Now, notice that we are only taking the deviations that are below the target. So this is the formula, and I'll show you how to use this formula given some data. We have return data for 12 months. So these are the numbers for the 12 months. We need to come up with the target semi-deviation where the target is 4%. So what we do is we take each of these numbers, the observation, and then look at how different this is from 4%. So in January, the observation was 6%. Relative to 4%, this is more by 2%, but this is more than 4%. So that's why when we are calculating the target downside deviation, we do not consider this number. In fact, all the numbers where we are at 4 or higher, we do not consider those numbers. On the other hand, when we are below 4%, such as over here, in March, the return was -2. So relative to the target, the deviation is -6. So we need to come up with all these numbers which are below the target value. And once we have these numbers, we take the square. So that's this thing over here, each number minus b. B is the target value, which in our example is 4. So we take the difference and square. So that basically removes the minus. And then we add all those numbers. So that's happening over here. We take each of these numbers and add them. That gives us 167 for this data. And then we divide by n minus 1. So an important point to note here is that n represents this entire data. With n, we are not just looking at the numbers over here. We are looking at all these numbers. So with n, we are actually looking at the entire data set. N is 12, so n minus 1 is 11. That's why we have 11 over here. And our target semi-deviation is 3.8964%. So the idea is that we use roughly the same calculation as what we do for standard deviation, but we only focus on numbers that are below the target value. The target downside deviation will be less than the standard deviation, and the reason is fairly obvious. With standard deviation, we are looking at numbers on both sides of the mean, whereas with target downside deviation, we are only focused on numbers that are below the target value. We are not worrying about numbers over here. Therefore, by definition, the deviation will be lower. So you need to remember this. Another point is that as the target is increased, the downside deviation will increase. Here we have a target of 4. What if we had set a target of 5? If the target is 5, then obviously the deviation of the different terms relative to 5 would be more. So we can say that as the target is increased, the target downside deviation will also increase. Next, we have the coefficient of variation. The coefficient of variation expresses how much dispersion exists relative to the mean of a distribution. So we might have two different distributions with different means and different standard deviations. Given that the means are different, let's say one distribution has a mean of 150 and a standard deviation of, let's say, 10, whereas another distribution has a mean of 5 and a standard deviation of 4. Now, we can't just look at 4 and 10 and say that A has a greater variation, because we also need to consider the mean. So relative to a mean of 150, a standard deviation of 10 is not very much, whereas relative to a mean of 5, a standard deviation of 4 is quite substantial. So basically, to look at how much variation we have per unit of return, we use the coefficient of variation. And the formula is given over here. We have the standard deviation divided by the mean. So this basically is the variation per unit of return. The X bar here generally represents the mean return. Now, if we have investment A with a mean return of 7% and a standard deviation of 0.05, and B has a mean return of 12% and a standard deviation of 0.07, which is riskier. To compare these two investments, we should calculate the coefficient of variation for both. So for A, the coefficient of variation will be the standard deviation, which is 0.05. We can write this as a percent. So we can have 5% divided by the mean return, which is 7%. And for B, we have the standard deviation, which is 7% divided by the mean return of 12%. So here we can clearly see that 5 over 7 is greater than 7 over 12. Therefore, we can say that A has greater risk. This measure allows for direct comparison of dispersion across different data sets, and it is used in investment analysis to compare relative risk. Now I want you to do this practice problem. Which of these assets has the lowest risk per unit of return? So this is fairly straightforward. All you need to do is take the standard deviation and then divide by the mean. So for A, that would be 4.9% divided by 16.4%. Do the same for all three. And the one with the lowest answer should be B. Here we will have the lowest risk per unit of return.